Today, we're going to talk about what might be the single most expensive software bug in history. Seriously, it's an incredible story about a massive rocket, a tiny bit of recycled code, and a failure that was, well, truly spectacular and very, very public.
Take a look at that number, $370 million. Now, that's not the price of the mission. Nope, that is the cost of a single software error. One mistake in the code that literally vaporized a decade of work in less than a minute. So how on earth does something like this even happen?
All right, let's set the scene. The date is June 4th, 1996, where in French Guiana and the European Space Agency is about to launch the brand new Ariane 5 rocket. This thing is an absolute beast, the result of 10 years of work and a $7 billion investment. It's designed to launch the next generation of satellites, and of course, the whole world is watching. The final countdown hits 0. We have liftoff, and for 36 seconds, everything is absolutely perfect. All systems are green, the flight path is nominal. You can just imagine the sense of relief in the control room. But then, at 37 seconds, the rocket suddenly violently swerves off course. The aerodynamic forces are so immense, they rip the boosters clean off the main stage. And just 2 seconds later, the self-destruct system kicks in. The whole thing is over in a giant fireball. So what in the world went wrong? Was it a bad engine? A fuel leak? A structural problem? Well, no. The investigation was surprisingly quick. It only took about 2 weeks to find the culprit. And it wasn't a physical problem at all. The entire catastrophe was traced back to a few lines of code buried deep inside the rocket's guidance system. To really get this, we've got to pop the hood and look inside the rocket's brain, a component called the inertial reference system. You can think of this as the computer that handles the rocket's sense of direction. It tells it which way is up, which way is down, and where it's headed. And the failure happened right inside this system's software. And here we have it. The root cause of a $370 million explosion was a simple data conversion. The software was just trying to change one type of number into another type of number. It sounds almost ridiculously simple, almost trivial, right? But as you're about to see, in the world of software, tiny details like this are absolutely everything. So here's the technical problem in a nutshell. The software was taking a very large, very precise number, what programmers call a 64-bit float, and it was trying to cram it into a much, much smaller container, a 16-bit integer. The best analogy I've heard for this is trying to pour a full gallon of water into a tiny pint glass. It's not gonna fit, and you're gonna make a huge mess. Now, you might be thinking, why would they even have code that does something like that? And here's the crazy part. This exact same piece of code had worked perfectly on previous rockets. But a change in the real world, the fact that this new rocket was much faster, created a mathematical problem that the old software was never, ever designed to handle. This specific type of error has a name. It's called an integer overflow. And that's exactly what happens when you try to stuff that gallon of water into the pint glass. The number that represented the rocket's horizontal velocity just got too big for the little variable that was supposed to hold it, and the computer basically had a meltdown. It just couldn't compute. And this right here shows you exactly why it failed. See, the code was reused from the older, slower Ariane 4 rocket. For Ariane 4, that velocity number never even got close to the maximum value a 16-bit integer can hold, which is 32,767. But Ariane 5, it was way more powerful. Its velocity blew right past that limit, and that's what triggered the overflow. So this is the heart of the matter. This was legacy code. The engineers basically copied and pasted a software module from Ariane 4, assuming that, hey, if it worked before, it'll work again. But they didn't retest it against the new, much faster flight profile of Ariane 5. And that assumption turned out to be fatal. But wait a second, a single computer crashing shouldn't take down a whole multi-million-dollar rocket, right? Shouldn't there be backups? Well, this is where a small bug snowballed into a total system collapse. It wasn't just one error, it was a catastrophic chain reaction. Let's just walk through this cascade of failure. First, the integer overflow happens. That immediately crashes the primary guidance computer. As it dies, it sends a final message, a stream of diagnostic data, to the main flight computer. But the main computer wasn't programmed to understand that message. It completely misinterpreted that diagnostic code as actual flight commands, commands for a huge and sudden course correction. The rocket's engines did exactly what they were told, swiveling violently, and the rocket tore itself apart.
And what about the backup system, the redundancy that's supposed to save the day? Well, it was running the exact same software. So, just 0.05 of a second after the primary system failed, the backup system hit the very same velocity, had the very same integer overflow, and crashed in the exact same way. The backup was completely useless.
So this disaster gives us some absolutely timeless and very, very expensive lessons. You see, the bug itself was a simple coding error, but the explosion? That was a catastrophic software engineering failure. And trust me, there's a huge difference between the two.
Okay, lesson number 1. You can't just copy and paste code from one project to another and assume it's going to work. Software isn't a brick. Its behavior depends entirely on its environment. Reusing code is a great idea, but it is incredibly dangerous unless you also retest it rigorously for the new conditions it's going to face.
Lesson 2 is all about assumptions. The original programmers assumed that velocity value would never get too high, so to save a tiny amount of computer processing power, they decided not to include any code to handle that possibility. But great engineering is all about anticipating failures, even the impossible ones. It's about writing defensive code that can handle unexpected situations gracefully, instead of just, well, crashing.
And the third and maybe most critical lesson, having a backup system is pointless if it has the same fundamental flaw as the primary one. True redundancy, especially in software, isn't just about having two of the same thing. You have to account for the possibility that the logic itself is wrong, not just that a piece of hardware might fail. And all of this brings us to one final, really interesting question. Who was really at fault here? Was it the programmer who didn't protect against the overflow? Or was it the system architect who allowed code to be reused without proper testing and who designed a backup system that was doomed to repeat the same mistake? It's a question that honestly changed how we think about building complex, high-stakes systems forever.